In this video lecture, we're going to be talking about decision trees. Decision trees are supervised machine learning algorithms that allow you to classify data, so classify labels in your data. So one example of a supervised classifier we have seen so far is the logistic regression. And decision tree basically is an alternative to logistic regression, and it's sort of doing the exact same job here. So let's first look at a very simple decision tree. Let's say I have a column called cat allergy, and if this is true, I'm going to label no, and if this is false, I'm going to label adopt, right? So this decision tree is basically classifying if a person is adopting a cat or not. And so I'm saying that if they don't have a cat allergy, then they will adopt. If they do, they're not going to. So a decision tree basically is going to be asking a question like this, and then based on the answers, so true or false, categorical data here, based on the answers, you are able to classify and assign labels to your data. You'll notice that this example currently uses categorical data here, so true and false, but we can also have an example of using numerical data to make decision trees. And that might look somewhat like this, where I can say number of cats is our variable that we're looking at, and if it's less than 5, then I am going to adopt a cat, and if it's greater than 5, then I am not going to adopt a cat. So again, based on a value of our numerical variable, we decide to have a cutoff, and then if the number of cats is greater than 5, then I'm not going to adopt a cat, and if it's less than 5, then I am going to adopt a cat. And again, here I'm still asking a question, and based on the results here, I'm classifying my data. Now that's a very trivial example of a decision tree, and we can sort of make it a little more complex by adding more nodes. So let's say I am trying to figure out if I need to eat, not eat, or eat just snacks. And so maybe I have a variable that is hungry, ? And if this is true, then maybe I split on very hungry. And so if very hungry is true, then I'm going to eat lunch. And if very hungry is false, I am going to eat snack. And then if I am not hungry, I'm going to add arrows here. And if I am not hungry, so if that is false, I am not going to eat anything. So in this case, again, we have 3 labels: eat lunch, eat snack, or don't eat. And based on the values, the categorical values of these variables, hungry and very hungry, I'm able to decide which classification I would have for this data set. So let's say I have a person who is hungry, but they're not very hungry. So what I will do is I'll say, okay, they are hungry, they're not very hungry, so they're just going to eat snacks. Or another person in my data set are not hungry, so we'll go down this lane, and because hungry here is false, and we'll say that they are not going to eat anything at all. So let's label these a little. So this guy, the very first node, is called a root node. And that's because it has arrows coming out of it, but not going into it. So that's basically a teller. We also will have a thing called internal nodes. And this guy's an internal node. And the idea behind internal node is that it will have arrows coming into it and arrows going out of it too. And finally, we'll have root nodes, not root. We'll have leaf nodes. And so this is a leaf node, that's a leaf node, and this here is a leaf node too. So again, their idea is that they will have arrows coming into them, like this, but they won't have arrows going out. That's basically the end of the line for your splits. And this is the general idea of what a decision tree is. Now, the main concept here to understand is how to go from raw data to a decision tree. Because when we usually use examples in our class, we don't usually get a data set in the form of a decision tree. We usually get a data in the form of a raw data. So we'll have a bunch of columns. So x1, let's say x2, x3, x4, and then we will have like a label. Let's just, for now, let's say yes, so yes, no, etc. And so the main idea here is to be able to convert something in the form of a raw data set into a decision tree that will allow us to classify and label our data correctly. So that's what we're going to be looking into. Here's a sample data set that I'm going to be using to create a decision tree, and here we're trying to predict if a student passes or fails an exam based on these four attributes. So we have whether or not student had breakfast, they slept well, if the professor was generous, and then a numerical variable talking about how many hours they studied for the exam. For the time being, I'm gonna skip out on the number of hours studies, and we're only gonna focus on if we're able to predict if a student passed an exam based on breakfast, sleep, and a generous professor. So the first thing we need to do when we're converting a raw data set into a decision tree is to find out what the root node is going to be. So either of these three could be our root node. And so to find the answer, we're going to first start by making three trivial decision trees where we're basically splitting on each of these categories to find how many passed or no passed we found. So what we'll do here is I'll split on breakfast. And if breakfast is true, so yes, we're going to count how many yeses or no of passed we got. And then if it was false, we're going to do the exact same thing. So yes and no. So here we're just going to count based on breakfast's true value. So 1, 2, 3, 4, 5. So for these 5 yeses for breakfast, I'm going to figure out how many yeses or nos there were. So 2 nos. Okay, so we have 2 nos, and then the rest will be 3 passes. And then for when breakfast was false, so let's do a different color here. The yellow ones, so 4 no's, and for each of them I had 1 yes, 1 no, 2 no's, and 3 no's. So 1 yeses and 3 no's. So again, here what I'm saying is that if I split my data on breakfast based on the categorical value of breakfast, so if it's true, then I had 3 students who passed, 2 who did not. And then based on the value of breakfast to be false, I had 1 student who passed the exam and 3 who didn't. And let's try to make another decision tree based on sleep, and then another one based on professor. So I'm going to do sleep. And again, these are categorical, so I'm going to say true or false. True just means yes, false means no. And again, we're going to count how many students passed or did not pass. Okay, so for sleep, I am going to again choose a different color, and I'm going to say, okay, true. So 1, 2, 3, 4. 4 in total were yeses, and for each of them I have 1 yes, 2 yeses, and 3 yeses, and 1 no. So 3 passed, 1 failed. And when sleep was false, which is 1, 2, 3, 4, 5 here, the yellows, I have 2 no's, 3 no's, 4 no's, so 4 did not pass, and then this guy passed, so 1 over here. And just like that, I can make another decision tree with just the professor. So again, here we're only trying to figure out which of these 3 categories should go as the root node. And this is a very important first step in determining that. So again, same idea. Yes, no, yes, no, and we're going to count how many professors, true, false, and again, we're going to count how many professors were generous. So we have 1, 2, 3, 4, 5, 6, okay. And for all 6, we're going to see how many were no's and yeses. So 1, 2 no's, and 1 yes, 2 yes, 3 yes. Okay, 3 and 3. So 1, 2, 3, and then 1, 2, 3. Yeah. And we're going to do the same thing with no's. We have 3 no's, 2 generous professors, and for each, let's check how many passed or did not pass. We have 1 yes, 1 no, and 2 no's. So 2 failed and 1 passed. Now, what we're hoping to find is that there was, ideally, a split where, let's say there were a split where this one was 0. Now, that is a really good split because then you can say that whenever a professor is generous, whenever this value is true, whenever the professor is generous, this is a yes, I will never have a student failing the exam. And that's crucial. You weren't able to classify every single data point here, but you were able to figure out that if the professor is generous, if they're ever generous, you are never going to fail based on this data set. And so let me go back here and let me do another example. Let's say if this thing was 0. So you have one of the categories for passes or fails as 0, and then you might say that, okay, if the student doesn't have breakfast, so if the breakfast value for the student is false, then they're only going to fail the exam. They're not going to pass ever based on the data set, because the yeses are always going to be 0 here. So what we're hoping to do is to find a split that will allow us to get that perfect node out there where at least one of these, or here or there or here, at least one of them is a 0. And once that's the case, then we'll say, okay, that is a pure node. And so if this were 0, you'll say that is a pure node over there. And that's what we're looking for in these splits. But you'll notice that none of these right now, if we were to split our data on breakfast or sleep or professor as the root, you'll notice that none of them have any pure nodes. So in that case, all of these nodes, so all these are called impure nodes because we're unable to find the purest ones out there that will give us a perfect split going on. So what do we do? Well, we weren't able to figure out if there were any pure nodes, but we could find a measure of how much impure, or the measure of impurity, for these nodes is. So what I mean by that is, let's say if the impurity level or the impurity score for breakfast was smaller than sleep or professor, in that case, I would say that breakfast should be our root node, because it gives us the lowest level of impurity, because we're trying to reach purity going forward. So if we are able to calculate and compare this impurity value, this guy over here, then we should be able to say which of these categories should be our root node. And that's basically the idea of a decision tree. That's where the math sort of comes in. So let's look at that. So there's multiple ways of calculating the impurity level of each split, and we're going to be using a thing called a Gini impurity score. Don't know where the name comes in, but we're going to be using this score value to determine which of these nodes, which of these splits are the best. So which of them have the lowest impurity, and that will slot in as our root node. So let's find the Gini impurity score for breakfast first, and I've copied these down again from the data set, and these are the counts for our classification label. So if the student had breakfast, it was true, then 3 students passed and 2 failed. And if the breakfast was false, the student didn't have any breakfast, then only 1 student passed and 3 failed. And again, that is being generated from the data itself. So the Gini score, let's do it in red, the Gini score is 1 minus the summation of all probabilities of the passed and not passed values squared. So the way we do it is we're going to first evaluate the Gini score for this left side node, and then the right side, and then we're going to find the average of the two for breakfast. So for the left node, the Gini score again is 1 minus the sum of all probabilities of yes and no passes squared. So 1 minus, so the yeses first is going to be 3 over, and the probability of yes happening out of all is 3 over 3 plus 2, right? 3 over 5, this whole thing, squared, plus the probability of no's, which is 2 over, and probability is out of the total, so 2 out of the total, which is 5 here, squared. And that will give us 0.36 plus 0.16, and finally you'll get a Gini score of 0.48. So that's the Gini score. That's the Gini score of the left node here. So I'm going to say Gini is equals to 0.48. Now we will evaluate the Gini score. We'll calculate it for the right node. And the same process is going to happen. And so we're going to say the Gini score is 1 minus the sum of all the probabilities squared of these passes and no passes. So the yeses was 1 over the total. So you have 1 over 4. Again, that's the probability of yes in this scenario, squared plus the probability of no's. So that's 3 over the total, which is 3 over 4 squared. And that should come out to be, just going to get the answer, 0.375. And I'm going to say the Gini score, the left node here, is 0.375. Now, once we've done that, we still haven't found the overall Gini score of breakfast, splitting on breakfast, the data. So you might think that we could just find the average of 0.48 plus 0.3575 divided by 2 and just get the average, but the problem here is going to be that this Gini score on the left node is for 5 students here. These are 5. And on the right node, we have 4 students. So this Gini score calculated is for more students than this one on less students. So what we'll have to do instead is not just do a basic average, we'll have to do a weighted average of the Gini scores. So what that means is that we'll find the total number of data points here, which is 5, divide by the total amount of students in this case. So it's 5 plus 4, which is 9. So I'm going to write it down separately, 5 plus 4. So that's the left node here, times its Gini score, which is 0.48, plus, now we'll do the exact same thing over the other side. So we'll say, okay, for the right-hand side, we had 3 plus 1, 4 out of 9 total students here, or 9 total data points. So I'm going to say 4 out of 4 plus 5 again, times that Gini score, the Gini score on the right-hand side, 0.375, and you will get, if you evaluate this, you will get a total weighted average Gini score of 0.43. So the Gini score, the Gini impurity score for breakfast, for splitting the data on breakfast as a root, is 0.43. Now, what we'll do is we'll evaluate the Gini score for sleep, and then we'll evaluate the Gini score for generous professor, and then we'll compare these values. So if the Gini score for breakfast was the lowest, so let's say the other two were 0.5 and 0.8, then we'll say that we're going to split on breakfast because it is showing the least impurity score level here. So let's calculate the let's do this example again, and let's try to calculate the Gini score for sleep. Okay, so I've written down the basic decision tree for sleep when for the entire data set if sleep is being used as the root, and again I have given you the count of passed. So if the sleep was true, 3 students passed the class and passed the exam and 1 failed, and if the sleep was false, 1 student passed and then 4 of them failed. So here's passed again here too. So again, we're going to be using the exact same formula. So we're going to say that the Gini impurity score is 1 minus the summation of all probabilities squared, the probabilities of each pass value, our label value. So again, we'll do it for the left node first. And should get some practice by now. Do this by hand, and you'll see that the Gini score here is going to be 1 minus, so the sum of the probability that passed was yes, so that's going to be 3 over the total, 3 over 4 squared, plus the probability that pass was no, so false, so we'll have 1 over 4 squared, and you'll get a Gini score of 0.375. And so I'm gonna put here Gini is equals to 0.375. We're going to do the same thing again for the right node. And again, we'll do the Gini score is equals to 1 minus, so the sum of all probabilities for passed. And you'll have, for the yeses, you'll have 1 over the total, so 1 over 5. That's 1 over 1 plus 4 squared plus 4 over the total, which is going to be 4 over 5 squared, and you'll get a Gini score when you evaluate this of 0.32. So the Gini score for the right node is 0.32. Next, we will have to calculate the overall Gini score. So again, for that, we will need to use the weighted average score, and again that would be the total on the right side, so the total on the right node, which is 4, divided by the overall total, so the total number of data points here, which is 9, so this is 4 plus 5, 9, times the Gini score on that side, 0.375 plus the weighted average over here is going to be 5, so 4 plus 1, 5, divided by the entire sum, so it's going to be 5 over 9, times the Gini score on the right side, which is going to be 0.32, and you will get a weighted average Gini score of 0.34. So we're going to say the Gini impurity score here is 0.34. So off camera, I was able to calculate the Gini score for professor, a generous professor, and it came out to be 0.48, and I'll let you calculate that as an exercise on your own. And we'll notice that the lowest Gini score from all these three categories was for sleep, so that will be our selected root node going forward. So now we can say that we're going to use sleep as our root for our decision tree, and based on its true and false values, we know that we can further divide the data on pass, no pass. So yes or no, and yes or no here, and it will look like 3, 1, 1, and 4. Again, the 3 is coming from, so let's do this example right away. So sleep true is 1, 2, 3, 4. That's why there are 4 of them. And for whenever sleep is true, we'll count how many passes there were. So 1 pass, and then 2 passes, and 3 passes, so 3, and then 1 no pass over here. And then when sleep was false, again, you'll have 1, 2, 3, 4, 5, so the total of 5. And for 5 of them, we had 1, 2, 3, 4. We had 4 no's, and let's see where the last one is. There's the 5th one, so 1, 5. So these are all the past values here. So we have now decided that for our decision tree, we're going to be using sleep as our root node because it had the lowest Gini score. But we're not going to stop right then and there. Instead, we're now going to start thinking about what should go here and which category should we split on here too. So we have already split our data on sleep, but we now have breakfast and we now have professor to then determine what should go here, what should we split on further to get a better decision tree. Because right now, even if we're just splitting on sleep here, it's not really telling us a good story. It's just saying that if you do sleep as a student, then 3 out of 4 times you're going to pass. That's not definitive. That's not good enough classification. So we're gonna keep splitting. So to do that, we're going to first again decide which node should go here. It could be either breakfast or it could be professor. And for that, we're going to make a trivial decision tree again. So I'm going to make one for breakfast, which is going to have a true and false value. And I'm going to also try to make one for professor with its own true and false value. So please remember that right now I'm only making these decision trees to figure out what should go here. What should this be replaced with, or further split maybe, based on these values. So the left node here. Okay, so to make that decision tree, to do this, we're going to still have our yes or no's on our past value, but now this split is coming from when sleep was in fact true. So we're going to first mark off when sleep was true. Yes, 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 yes. Okay, 4 of them. And then on top of that, we're going to find out which of the students had breakfast. So for these red marks, we have 1, 2 students. who had breakfast, and for those, what were the yes and no values. So I'm going to go and see that is a 1 yes, and that's another yes. So it should become 2 and 0. And let's try to do the example again with the false part. So again, because this is a split on top of when sleep was true, I'm only looking at these 4 values. And now I'm going to check what happened when breakfast was false. So I have 1, 2 where breakfast was false. And then based on that, I have 1 yes, and I have 1 no past values. Okay. We're going to do a similar thing with professor here too. But before that, I also want to compute the impurity score here. Because again, the idea here is once you have decided on a split as a root, you're going to then figure out what split you're going to make here. And then once you've decided on that, maybe you want to figure out what split goes here, what split goes here, and you continue on from there. And then you look at the right side node and you do the exact same thing. Again, the idea here is to have a decision tree that somehow gives us pure leaves, maybe. If not, the one that gives us the most credible information, so the least impurity score going on. So we're going to continue this example, and we're going to look at breakfast from when sleep was true and find the Gini score based on this data. So I'm going to start naming them again as my left node here. So this is my left node, and this is my right node. And based on that, again, I'm going to calculate their separate Gini scores and then find the weighted average. So let's find the Gini score for the left node here. And again, it's always going to be 1 minus the summation of all probabilities squared. And so for the left node, it is going to be 1 minus. So the probability of the yes for pass, so it is 2 over the total, which is 2 over 2, squared, plus 0 over the total, which is 0 over 2 squared. And this will come out to be a very beautiful 0. And for the right node, we're going to do the exact same thing. And once you solve it out, you'll get a Gini score of 0.5. So I'm going to put a 0 here and a 0.5. And again, if you do the weighted average now, you will get, so you'll have 2 over the total. So 2 over 4 times its Gini score, the left node is 0, plus 2 over the total, so 2 over 4 of the right node, and the Gini score is going to be 0.5 here, and you will get an overall weighted average for breakfast inside sleep to be true to be 0.25. So the Gini score here is 0.25. Now, the overall weighted average Gini score for professor needs to beat this 0.25 score here to be able to then get slotted over here. So you will going to eventually say that we split on sleep first, and then when sleep is true, we might then split on professor. One cool thing I want you guys to see here, notice here, is that this is a pure leaf node here, because you now have 2 yeses and 0 nos. So think of it at the moment, assume that breakfast split, this guy was over here. So you can now say with surety based on this data that when sleep is true, and then when breakfast is true, when sleep is true, you only have students who are going to pass the exam. You're not going to have any student who are going to fail the exam. And that's a pretty cool thing. You're able to now classify that if a student slept and they had breakfast, it doesn't really matter if the professor was generous or not, and it doesn't really matter how many hours of study they had, they're always going to pass that test. And that's why it's cool to have a Gini score of 0. What that means is basically that there are no impurities. This is a pure leaf node here. And that's sort of what we're looking for when we solve through this decision tree. let's now calculate the genius score, the average weighted genius score for when we use professor as a split for sleep equals true. So I'm going to again make the boxes for yes or no for past, and yes or no again for past here. And we're going to go back to the data and sort of try to figure out what values go in here. So again, this is when sleep is true again. So if sleep is true, we still have those 4 red dots here. We're going to check now if the professor was generous or not. And if the professor is generous, that is true, that is yes. So we have 1, 2, oh, that's not 1. We have 1 and 2. We're going to notice that they both have a yes value for past, so 2, 0. And then we're going to do for when professor was false, so we have 1, 2. And for that, we have 1 apiece for past, so 1 and 1. So very similar, well, exactly identical to how breakfast was being broken. So you don't need to calculate the genius scores here because you already know what that's going to be. It is going to be this genius score, the weighted average. It's going to be 0.25 because the genius score on this left node is going to be 0, and this one is going to be 0.5 because we've already calculated it before. So you now have a genius score for breakfast to be 0.25 and for professor to also be 0.25. Now this is a good example of what happens in the scenario, that you now have 2 variables that have the same impurity score. That is, they're sort of distributing the data in the same manner as to keep the purity level the same. So in that case, you can just pick either one. Because they're both giving you the same score here, you can just pick either one to slot in here. So what we'll do is we're going to put breakfast in there. So what happens is that I'm going to get rid of this left node that we were looking for. And instead, we're now going to say that it is in fact being split on breakfast now. And then it is further divided into this. So true, false, and we'll get a yes or no value for past, yes or no value for past here too. And you'll have 2, 0, and then 1, 1. So I've just basically copied this entire box chunk and put it up here. So what our decision tree now is that at the root, I have sleep. And whenever sleep is true, I will then split on breakfast. And then when breakfast is true, I have these values right now, but then I will have to go back because I still have professor remaining. I split on sleep and breakfast. I will now go and check if this node here can be further split on professor, and if this node here can be further split on professor. I'll add that I'm not going to split this node any further because it is already a pure node. You'll notice a 0 here. This will always give you an impurity of 0, so it doesn't really matter. It doesn't make sense to be further splitting it. But I can definitely split the false breakfast again to see if I'm able to split it on professor and get maybe 1 or 2 pure nodes. So let's look at that. So I'm going to try to split this right node where I don't have pure leaf nodes anymore to sort of see if I can split it on professor here. So I'm going to write professor, and I'm going to try to split on the true and false values of it. So true and false. And we're going to see the counts for the past are labels here. So now again, we'll have to sort of follow this trajectory here. So we're first going to find all the sleeps that are true. So sleep that are true is 1, 2, 3, 4. And then for that, we're going to split it on when breakfast is false. So For all of them, breakfast false is here and here, so not these two. So we're technically looking at these two rows here. So for those two rows, I have a professor value both of no, and for each of them, so there is no true, so I'm going to put a 0 and a 0 here, and there is a false one, so no's, and that is 1 apiece. Okay, now you'll notice that something like this happens, and you might start assuming that this is a leaf node because both of them are 0, so there shouldn't be any impurity score. But problem here is, if I do try to, in fact, calculate the Gini score here, again, that's going to be the sum of all probabilities of past squared, some problematic things are going to happen, because the probability of this thing of past being y here is 0 over 0 squared, plus of no's being 0 over 0 squared, and division of a number by 0 isn't possible in this scenario. So in that case, at this point in time, you're going to say that you've gone too far. And instead, you shouldn't be splitting on professor here at all, because this is mathematically impossible to compute, and so you're not able to get a Gini score or compare a Gini score over here. So in that case, you're going to say that I don't actually need to split this node furthermore. It is impure. We don't have a pure split like this here, and that's perfectly fine, but I'm not going to split it anymore. So if your sleep is true and your breakfast is false, then you have a 50-50 chance of a student passing or failing, compared to just have a non-calculatable value instead. So what I'll do is offline, I'll try to finish off what this tree should look like at the very end. So we're sort of now said that we have compiled the entire left side of the tree, but offline I'm going to compile and compute and give you the right hand side, and we'll look at the final table in a bit. So this is the final decision tree that I get using breakfast, sleep, and generous professor as a predictor for classifying if a student passed or failed an exam. So let's run through this real quickly. I was able to split on sleep as the root node, and was actually able to find breakfast to be both main splits on sleep, true and false. So two cool things to note here is that if, based on this data set, if a student slept and they had breakfast, then they're always going to pass a test. It doesn't really matter if the professor was generous or not. And then if a student failed to sleep and they did not have any breakfast, they're always going to fail the exam. It doesn't impact how many hours of study they had or what kind of professor they had. So we were sort of able to predict precisely a little if a student was going to pass or fail based on some values of our sleep and breakfast. But on the other hand, of course, you'll notice that if a student did sleep but didn't have any breakfast, then you have sort of a 50-50% chance of them passing or failing. And if the student didn't sleep and had breakfast, then they're more edging towards failing than passing. But we weren't able to definitively say which of these might happen. Now, you might be wondering that if you had a lot of features, so you have multiple, more than 4 or 5 independent variables, you might be thinking, I can just start splitting on everything. But that sort of might lead to overfitting of your model, because in that case, if you kept going in this direction, let's say, you kept splitting whenever this was false and false and false, you might end up with your past values being either 1, 0 or like a 0, 0 or a 0, 1, let's say. So if you're splitting your data so much that you're ending up with these little blocks, these tiny little leaf nodes where you only have one data point, that is sort of overfitting your data based on the data set. So instead, what you want to do is be able to stop at some point where you still have enough meaningful information going on. And what that'll do is, if you have more data coming in that you haven't actually trained your model on, then your decision tree might perform better on that new data set compared to if you split too much and overfit your model. Lastly, I want to add that if I were to use hours of studied, what I would do is maybe, let's say, I'll do hours studied. And then I could split on, let's say, greater than 5 and less than 5. Now, in that case, again, you will be calculating the pass and no passes, and you're going to evaluate a Gini score. But then what you could also do is change these. So instead of saying greater or less than 5, you might end up looking at greater than 3 and less than 3, or greater than 2 or less than 2. So you might want to work with different values of your cutoff here. So this cutoff here, to get an optimal value of the Gini score. So maybe you try with a cutoff of less than greater than 3 and you get a Gini score of 0.2, and then you try it with so this is when you're splitting on 3, and what if you had a cutoff of 5 and you get a 0.12? And so in that case, you'll say, okay, I might end up using this 5 as a cutoff for my decision tree. But again, what I usually do is I'll use the average, the mean or the median value here as my cutoff and see what happens, basically. But I'll leave that as an exercise for you guys to sort of now not only use these 3 to make a decision tree here, but instead use all 4 attributes and try to come up with the best decision tree that is able to predict if a student passes or fails.